All right, here we go. So let's talk about particle motion. I'm on page 24, 3.4, velocity and other rates of change. So let's see how much of this we can get through. I might have to make 2 videos for this, sets of notes. So in calculus, we discussed 2 different types of velocity, average velocity and instantaneous velocity. This distinction is a huge important concept from chapter 2. I'm not going to have you talk to a neighbor to briefly summarize the difference and give an example. I'll do that for you. So we talked, it was chapter 1 in this book. We talked about the difference between saying I went 60 miles in an hour, so my average velocity was 60 miles per hour, versus saying I am currently traveling 65 miles per hour. And we talked about the fact that in that 1 hour average velocity example of going 60, we are not going 60 the entire time. We may be going 62 at one moment and 58 at another moment, but the average over the entire interval is 60 miles per hour. Instantaneous is exactly what it sounds like, at that instant in time. Velocity is different from speed. Velocity is a vector. It has a direction. So velocity can be positive or negative. Typically positive means traveling right or up. Negative would be left or down. Speed is the absolute value of the velocity. Write that down. Speed equals absolute value of velocity. So it doesn't give us any indication of direction. It is not a vector. It is just a quantity. Acceleration is the derivative of the velocity. So I think we know enough to say we talk about s of t as the particle motion. That's the function that represents the particle motion. And v is the derivative of s, is the velocity of the particle. And a is the derivative of v, or the second derivative of s, and that's the acceleration. So the definition of acceleration, back in the notes. Acceleration is the derivative of velocity with respect to time. If a body's velocity at time t is given by this, v of t, which is the derivative of s, the derivative of the position function, then its acceleration is the derivative of v, or the second derivative of s. Hopefully you remember that notation for second derivative. Acceleration measures how quickly a body's speed increases or decreases. Okay, it's not talking about the position, it's talking about the speed. Okay, so give an example of positive, negative, or zero acceleration. Positive acceleration would be my foot is actually pressing on the gas pedal. Negative would be my foot is pressing on the brake pedal. And zero would be I have cruise control on. Okay, so first example, page 25. A particle moves along a line so that its position at any time t is given by this. So this would just tell me where it is. Like thinking of traveling on a number line. That's all we're talking about, is a particle moving back and forth on a number line. We can't do anything in 3 dimensions in this class because we only have 2 variables. So we cannot have a particle going all over the place. It's straight back and forth on a number line. They always say t is greater than 0. I think that's a gift. Time can't be less than 0, so I think that's a little silly, but whatever. So t is measured in seconds and s in feet. Let's play around with some numbers to try to get a feel for the motion. So let me write this down. Okay, so probably want to know where my particle starts, right? So maybe plugging in a 0 for time would be a good idea to give me a starting point. And we can see 0, 0, 0, so it starts at negative 14. So again, we're talking about motion on a number line. So here's my number line, here's negative 14, this is where I start. I don't know anything other than that at this point. So maybe I want to know where I go. So maybe I want to plug in like a 1. So I would have what? 1 minus 8 plus 24 minus 14. Okay, so here's where you're going to see that I'm on pain meds. What is this? Negative 9 plus 10, that's 1. I'm going to double check that. That is not negative 9, that's negative 7. Plus 10. Okay, so after only 1 second has elapsed, it's all the way over at 7. So just from my information, I know that it traveled to the right. Okay. So based on what we said about velocity, we know traveling to the right, this would have a positive velocity between t equals 0 and t equals 1. So we're going to finish this diagram, but we were just playing around a little. What's the difference between displacement and distance traveled? So this is a big difference. So huge important concept from chapter 1 was the difference between average and instantaneous velocity that we just talked about a minute ago. Another pretty important distinction that comes up quite often on the AP exam is the distinction between displacement and distance traveled. Displacement is just from beginning to end. So the ending point minus the starting point. Distance traveled, well, if I'm boring, and usually I would show you this walking around class, if I'm boring and I just go from here to here, displacement and distance traveled are going to be the same. But so let's say that this is a t equals a. What if I did something else though? Let's say I haven't gotten through all my time and I go back and then I go back there in my time interval from A to B. Now, there's no way for me to kind of do a back and forth motion without showing some overlap here. Otherwise it would just look like a big ugly messy line, right? So the particle is not swerving up and swerving down. It is staying straight back and forth and back. But if you notice, the displacement would just say whatever this number is minus whatever this number is. It would literally just give me that length. That is often, more often than not what I want. More often, I want to know exactly what I traveled. So I need to find the length of this, plus the length of this, plus the length of this, to get the distance traveled. And we'll talk about how to do that. So back to this problem. Find the displacement after 5 seconds. So that's easy. We have a formula for that. The displacement after 5 seconds would be f of 5 minus f of 0. The time interval goes from 0 to 5. So ending position minus starting position. I'm not going to be able to do that. Well, we're talking about an s in this problem, right? So I would literally plug in 5 right here, and then I would subtract the s of 0. So I'll write it out, but you guys are going to need to do this on a calculator. I'm not going to be able to do this. So that would be s of 5. Let me grab a different color. That would be s of 5. And then I would do minus s of 0, which we already figured out, but I want to write this out so you have it. S of 0. So, whoops, I put the minus in the wrong spot. Minus right there. So 0 cubed minus 9 times 0 squared plus 24 times 0 minus 14. So that would be literally the displacement, whatever that quantity is. Okay, part B says find the average velocity during the first 5 seconds. So hopefully you remember, or maybe it'll come back to you. From chapter 1, the average velocity, we wrote it as an F again. This problem is an S, no biggie. That's the formula for average velocity. So for this one, we would do S of 5 minus S of 0 over 5 minus 0. So literally we're taking this answer and dividing it by 5. So, and this would now be, do we have units in this problem? We do have units. If you go back up to the top, it says S is measured in feet. So whatever we got out of this, whatever numeric value, we would say feet up here because that's a distance. Displacement is a length measure. This is now feet divided by seconds because these are measured in terms of time. And the problem told us that the time unit is, the time measurement is seconds. So we would get feet per second here. That's the average. And then the last one on that page says find the velocity. So part C. So let me rewrite my S of t. I'm sure you guys have figured this part out. The velocity is just the derivative. We talked about that. And it says at time t, so they just want it with a t. And you're done. Okay, that's already 10 minutes, so I'm gonna pause it and I'll make a new one. Not pause it, but stop it.